Hi everybody, welcome to Periodic Trends Among the Elements. My name's Ethan.
And this is Dr. Mood.
Alright, so we're going to start off first by half filling a 250 milliliter beaker with tap water. Okay. Spilled a little bit on the side, that's okay.
And why are we doing this?
Well, you'll see we're about to fill a 16 by 150 test tube with water as well. And we're going to invert it and flip it into the beaker. And you'll see when we do it the reason why. It's a little tricky. All right, so about 3/4 of the way we'll do it. And here's the tricky part. All right, so see how we were able to trap some of the water into the test tube? And again, this will become evident in a few minutes why we did this. So now we're going to use dry tongs, emphasis on dry, to obtain a small piece of calcium metal. It has to be dry because calcium, as we'll see in a bit, reacts with water.
So how does calcium react with water?
Well, calcium causes water to go through hydrolysis. So it breaks water into, takes it from the HOH, breaks it into just some protons, which then turns into hydrogen gas, which you can see bubbling off right there, and then hydroxide, which is the OH, and you can see we're getting a lot of hydrogen gas there. So we've sped this up a little bit. We're trying to collect a full tube of gas, and once we feel like we've gotten a good amount, we're going to take it out, and we're going to make sure that it is hydrogen gas. We have no idea just by looking at it. It's some kind of gas, but...
So how are we going to do that?
Well, we're just going to light a match. And hydrogen gas, very explosive. And that's hydrogen gas right there. So, and we'll test the water in a bit because... And we've got a nice slow replay. But like I was saying, if this is true, this is hydrogen gas, that means the water also left behind some hydroxide ions, which is very basic. So if we test the water later and it's basic, and that's beautiful. Perfect. And let's test it, yeah. So we'll use some red litmus paper.
Turn blue.
Turn blue, so it's basic. There we go. Water broke into hydrogen gas and hydroxide.
Just remember litmus paper is always blue and basic. You can remember B starts with blue, basic starts with blue.
There you go. And then red if acidic. There's not really a good acronym or way to remember that, but process of elimination, right?
Yeah, it's only two options.
Okay, so we're going to do the exact same setup. This time we're going to be doing it with sodium. We're going to see if it's more or less reactive. Okay, we've got our nice setup. Sodium metal we actually keep in mineral oil because it's so reactive that it will just react with the water in the air. So we'll get a real small piece. We're going to cover it with tin foil. All right. And it's like we're at Chipotle, right? Wrap it up.
Yeah, if you didn't do this, you would just get a very giant flame on top of your water, which is a little dangerous. So we're going to try to minimize that.
So sodium, if you just put it in water and you get a huge flame, do you think it's more or less reactive than calcium?
I would say more.
More, yeah. Calcium didn't just catch on fire spontaneously. So and this is you can see why we put the water in the test tube like that. It helps just keep it up and float to the top. It's pretty cool.
And so since we put it in tin foil and there's kind of that oil layer that's still around it, it's going to cause the sodium to react slower than it normally would, but that's just a safety precaution.
And again, this is sped up, but pretty cool. You can see as that hydrogen gas, and there's a lot of it, is being produced, it actually pushes the water layer down.
I think part of that also is usually these metals will form oxides on them. And once you start getting into it, now you have a bunch of fresh metal on the outside to start reacting, so it kind of speeds it up.
And again, let's just make sure that this is hydrogen gas. That flame is getting very close to my fingers, so we're trying to hurry up. And, all right, I saw a little pop there. Let's see if we could do an instant replay in slow motion. And you can kind of see the gas sneaking out. Oh, catches the flame, and that's beautiful. So yeah, definitely hydrogen gas. Again, we're going to test the water left behind and see if it's basic. And it's basic. It's blue. So again, we had hydrogen gas and hydroxide ions floating around. All right, so now we're going to do it with potassium. Usually if you guys were in the lab, we'd actually have the lab instructors do this. Thankfully, we're 2 lab instructors, so we could do it on our own. And you'll see why in a second, why this isn't something that every student can just do on their own. If you're kind of picking up with the trends of this video, right, periodic trends, we're getting a little bit more and more reactive. So my guess is that this is going to be very reactive. All right, so we have some potassium metal. And yeah,
it's on fire.
It's on fire. So we have the slow motion up in the left-hand corner. Pretty cool. It's spraying out some metal chunks. Some of it got on the camera. That's okay. We'll clean it up. Now here's another replay. And this time, if you see this pink color coming off, if you guys remember from acid-base titrations, we use this compound or this indicator called phenolphthalein, which anytime it's in a basic solution, it turns bright pink. So actually you can see in this slow motion, we have our potassium metal on the water, and you can actually look, you can see the flames coming off from the side that's not even touching the metal. That's where the hydrogen gas is being produced, and that's where the flame is going. And then underneath, we actually know that, and there we have some more cool explosions, that we have the hydroxide floating around in solution because of our phenolphthalein.
And if you guys want to just look up cesium in water, you can see this trend even more as you go down the periodic table.
All right, so now we're going to be taking some more metals. We're going to be placing them in test tubes with water and seeing what happens. We're going to be checking for bubbles, and bubbles would be kind of a hint that some reaction is happening, hydrolysis perhaps, and hydrogen gas is being created. Or if there's no bubbles, we can say that no reaction is taking place.
You see any bubbles?
Not yet. Kind of far away though.
Yeah.
So after we get all 3 of these set up, we'll zoom in the camera and we can get a closer look. Again, this isn't the most exciting part of the lab, but it's pretty good to understand, figure out the trends. Here we have sulfur. It's a nice yellowy powder. It does not smell good. All right, so this is a 30-minute time lapse. Really not seeing much going on. You can kind of look and see bubbles on the surface of some of the metals, and we'll probably get a closer look in a sec as well. All right. So you can see some bubbles on the surface of the metal, very few. I would say I don't really see any on that one.
I don't see any.
And then nothing.
Nothing.
All right, so now we're going to take our period 3 elements and we're going to react them with hydrochloric acid. So you guys are getting familiar with this setup. We're going to fill up a 250 milliliter beaker with some water, do the same thing with a test tube, invert it, and trap some water in there. So basically we're doing the same thing as before, but now we're adding hydrochloric acid. Dr. Mood, do you think that's going to change anything in this reaction?
Yeah, I think it will have a different reaction.
All right. I like that prediction.
Different reactant. Different reaction. So hopefully you remember from class what happens when you add pure metals to HCl. What do you form? Something to think about.
And as you guys can see here, we're adding acid to water. That's the way to do it. That's the way you're supposed to do it in the lab. And if you want to remember, you can say, do as you oughta, add acid to water. Dr. Muda, have you ever added water to acid?
I have. I just kept it cold.
Yeah.
It works. Just, especially if it's a small quantity too. Anyways, but yeah.
Yeah, just good rule of thumb. All right, so as you can see, we have some bubbles forming. Again, pretty good indication that we have hydrogen gas forming. All right, so it looks like our hydrochloric acid is kind of giving this reaction, how could you say, like a kick in the pants. It's helping it along.
Speed up.
Speed up. All right, so we sped past some of that. Now we've collected a tube full of gas, and we're going to see, again, using our good friend fire, if we get a combustion, then yes, we formed hydrogen gas.
There it is.
And you can see that kind of caught me off guard. All right, so we're going to be using magnesium, aluminum, and sulfur in 3 test tubes like we did before when we checked for bubbles. But this time, we're going to be putting 3 molar hydrochloric acid in each of the test tubes. All right, and so you can see our previous run on the left-hand side of this test tube rack. And this time we'll set it up on our right-hand side.
So before we add it, think about what you think is going to happen.
I mean, this is, again, sped up, but you can already see.
It looks different.
Yeah, that magnesium it's going. Aluminum, we'll have to take a closer look. Same thing with sulfur, can't really tell from up here.
Well, that magnesium's definitely sped, going a lot faster.
Absolutely. Aluminum, I can see some slight bubbles.
Yeah, they're there.
Sulfur?
I don't really see anything.
I'm not seeing anything.
Our magnesium's almost gone.
Now we're going to be testing the elements across the third row of the periodic table. We're going to test these compounds or solutions with pH with a litmus paper. For each solution, we're going to touch the dropper to the litmus paper, record our observations in the table below. So I just set up some red litmus paper and some blue litmus paper so I can test on each one for each solution. All right, so if red turns blue, it means it's basic.
B for basic. Still blue.
Still blue, so it's basic. All right, magnesium hydroxide.
Before we add it, think about whether you think this is going to be acidic, basic, and then see if you're right.
All right, blue staying blue. Pretty good hint that. All right, now we have aluminum sulfate.
I wonder what that's going to be.
Okay, so this time we have red staying red. All right, and our blue went red as well. So,
what does that mean?
What does it mean? We're not. Now we have phosphoric acid. Do you think it's going to be acidic or basic?
I don't know. It has the word acid in it, so.
Red staying red, so that's a good sign.
And blue is turning red.
Red as well.
So you should be able to figure out what that means.
Yeah.
Sulfuric acid.
Red to red. And blue to red. Easy enough. All right, now we have some methanol. All right, so we had red staying red.
And blue.
Staying blue. What could that possibly mean?
Maybe it's...
Not acidic nor basic?
Could be.
What could that mean? All right, now we're going to check out amphoteric behavior. All right, so we're going to use aluminum sulfate. And as we're setting this up, start to ask yourself, what does amphoteric mean?
Is it kind of like amphibian?
So we're going to take some blue litmus paper right off the bat and just test to see the pHs, okay? Blue to red. Okay, it's acidic. Easy enough. So we're starting off with an acidic solution. Now we're going to take our good friend sodium hydroxide, which is a very basic solution. If we're adding base to an acid, the more base we add, it should become more and more basic. Okay?
That would make sense.
See, we kind of get a precipitate there. I'm going to add some more sodium hydroxide. All right, now we're going to take our blue litmus paper again and let's test it. If it's still red, then it's still acidic. But if our blue litmus paper stays blue, then it means that the sodium hydroxide that we added made it basic. And there you go, blue staying blue. So that sodium hydroxide we added made it basic. All right, we're going to test it with our red litmus paper just to be sure. I always like to double check these things. So again, we think it's basic right now, so if we add red litmus paper to it, it should change blue, right? And there we go.
It's blue.
Very strong blue. All right, so here's where the cool thing about amphoteric behavior comes in. We're going to add more sodium hydroxide. This time it's a little bit stronger, it's 6 molar. We're just going to keep adding basic solution to it. So sodium hydroxide, remember it's a base, adding some more in. What's going to happen? Well, we would assume that it would just become more and more basic, right? We start to see something weird happen. Our precipitate starts to dissolve, become soluble again. All we did was add more base. The same base, in fact, just stronger. All right, let's check. All the precipitate's gone. What could this mean? Well, not really quite sure right now, right? Let's just test it. Remember last time, before we added more base, our red litmus, whoa! We just put in red litmus paper and it's blue. So it's still basic.
Makes sense. I mean, if you're adding concentrated base
Right.
to an already basic solution, it would stay blue.
Yeah. Okay, blue staying blue, still basic.
This is Dr. Mood. We'll see you guys next time.
See you guys.